Hi guys, hope all doing good. Welcome back to the next lecture, lecture 2.1 of the course Crash Course on Strength of Materials. In this session we are starting the next chapter, second chapter on simple stresses and strains. In the last chapter we have concluded our discussion with all the basic prerequisites for this course. Now we'll go into the bit deeper concepts with main definitions starting in this video. Initially, in the stress strain diagram in the earlier classes, we have discussed that in the linear region of a stress strain diagram, for any stress strain diagram for any material, whatever extent possible, depending on the material property, there will be certain linear region within elastic region. Up to here, for example, it is elastic region. Up to this point it will be a proportionality limit where sigma and epsilon are directly proportional. So this linear part comes under Hooke's law, and Hooke's law states that for homogeneous isotropic materials, stress is directly proportional to strain, linear relation. That means sigma is directly proportional to strain. Epsilon. Now this is directly proportional symbol, implies sigma. When I convert this proportional symbol to equal to, then proportionality constant should be included there, E into epsilon. This E is called proportionality constant, which is called Young's modulus, and epsilon is, anyway we know, strain, sigma is stress. Next one is Poisson's ratio. We have earlier discussed in that stress strain diagram of mild steel itself that when a certain object, a certain body is subjected to certain load in one direction, say it is a longitudinal direction, then there are stresses generated, and accordingly strain is generated because it changes in length. Because I am showing tension here, it is increasing in length. If it was a compression, it would have been decrease in length. Proportional to whatever it is, here since length is increasing in one direction, in the applied load applied direction, in the perpendicular directions or any other directions, accordingly the dimension will decrease. The dimension in this direction is increasing depending on this load. If it was a compressive load, this dimension along this load, since it is a compressive load, the dimension along this direction would be reduced. This is the reduction or decrease due to compressive load. Now this is increase in the length due to tensile load. Whatever it is, there is change in dimension in the direction of applied load. Now this is for suppose this is longitudinal direction or applied load direction. Now there is certain due to the increase or decrease, whatever it is, there decrease or increase, there is certain strain happening. Let us name it longitudinal strain. When due to that longitudinal strain, we have already studied that since this due to the conservation of volume, since the same volume has to exist this case and this stage as well, that means when length is increasing, automatically area of cross section decreases. That means automatically this dimension reduces in this case, or else this dimension increases in this case from stage 1 to stage 2, depending on the load applied, compressive or tensile, whatever it is. Now since this dimension is decreasing, there is a negative sign applied, and the decrease in the for example, this is a longitudinal direction. Any direction perpendicular to the longitudinal direction is called lateral direction. Now generally, since we follow only 3-axis system, x, y and z, if this is x, vertical is y, and out of the plane is z. So this y and z planes will be axis will be lateral axis for this particular body. So strains along those axes, y-axis and z-axis, will be lateral strains. Now since along x-axis, that is longitudinal axis, there is increase, positive strain, there will be negative strains, I mean reduce, that means negative strains along lateral axis. That's why since mu is a Poisson ratio, and generally for engineering materials we consider it to be positive, for making it positive, to compensate that negativity in the lateral strain, we multiply it by minus, so that overall value will become plus, because anyway longitudinal strain, considering that it is under tension, longitudinal strain is positive, lateral strain is then that case negative, so negative by positive is overall negative, negative of negative is becomes overall value positive. So that is one thing you need to understand. If at all, for example, this is the case, compressive load case, then longitudinal strain will be negative. When due to compression, if length you are decreasing, then automatically area of cross section has to increase. That means diameter will increase. That means lateral dimension is increasing. Automatically lateral strain will be positive. So positive by negative gives us a negative value. Negative of negative again will give us a positive value. So whichever is the case, this mu will be positive for all our engineering materials. Engineering materials in the sense, if in one direction, if the for an applied load, if in one direction is in if an load is applied axially, in that direction, if the dimension is decreasing, then in the perpendicular direction the dimension will increase. If dimension is increasing in the perpendicular direction, the dimension will decrease. So it will be opposite. For a tension, in tension, when it is in tension, automatically in this direction, since tension is in longitudinal, so longitudinal strain will be positive. Then that's the oppositely, for transverse case, strain will be negative. Opposite, if longitudinal is compressive load and that direction implies strain is negative, that means in lateral direction strain will be positive. So opposite, lateral and longitudinal strains will have opposite directions. I mean, if it is positive, this will be negative. If it is positive, this will be negative. That's what I want to say. For engineering materials, for all our engineering materials. Hope you are clear with that. And generally for all engineering materials, the value of mu lies between 0 and 0.5. So first, materials like steel, when I say steel, then mu steel will be around 0.3 approximately, and say another material cork, it will be 0.5. There is certain prominence for this, I will discuss it later. Now coming to next definitions. Earlier I have already discussed that when there is a force applied on any material or a object or element, there will be certain deformation delta. Now when there is certain deformation, as the force increases, the deformation increases. Either it is a tensile force or normal force. During tensile and normal force conditions, deformation is in dimension, that is length dimension, increasing or decreasing. If it is shear force, the deformation is in the form of shape change, that is distortion of the shape. Whatever it is, certain deformation is happening. Now as the deformation is happening, molecules or atoms have to change their positions. That means displacements are taking place within the element volume, then or points of the volume. Then due to the displacement, due to the external force done or applied, there will be certain work done on the elements or on the element volume, work done on the element volume. Due to that work done on the element will be stored as strain energy in the material. That is, when this strain is happening, strain is due to the external applied load, that when the material is strained, then the energy is absorbed by the material due to the work done on it. That energy absorbed is termed as strain energy. Now when this strain energy we are measuring is related to the amount of strain that occurs. Now up to the we already studied in stress strain diagram that there is certain proportionality limit. So this is a proportionality limit. Up to at this proportionality point, stress is sigma PL, that is stress at proportionality limit, and this is strain at proportionality limit. Within this, when we are counting or considering the energy absorbed within this limit, that means below this limit, either loading is up to here. If loading is up to here, then energy stored we will consider up to here. If loading is up to here, that means this is stress and this is strain values correspondingly, then we will consider energy stored up to this point. So whatever it is, from 0 to below this proportionality limit, the energy absorbed will be called as resilience. When that limit we are increasing up to the proportionality limit, that is maximum level at up to the proportionality limit, then energy stored up to that complete final point, I am not talking about this one, and within proportionality limit maximum possible is up to here. Up to there, whatever energy is stored within the material, absorbed by the material, that is capacity of the material to, sorry, not up to proportionality, up to elastic zone, up to elastic zone. Up to elastic zone, whatever energy that can be absorbed by the material in the elastic zone, that is called proof resilience. That means maximum energy absorbing capacity of material in elastic zone. Similarly, resilience, by mistake I told about proportionality limit, not proportionality limit, up to elastic zone. Up to elastic zone. So those are the things to be discussed with resilience, strain energy and proof resilience. Now modulus of resilience is this proof resilience up to this elastic zone, whatever is the maximum energy that can be stored, divided by the volume. That means half force into displacement is the actual energy, and if it is up to elastic zone or elastic limit, within the elastic limit maximum possible things, then this half Fe into delta is the maximum possible energy that can be stored, maximum possible or maximum capacity of the material to store the energy up to within elastic zone. Now if it is so, then divided by volume. When I say volume I can write something like area into length. There will be certain length for the element, we can consider it as like that, and certain area of cross section. Now when I say that, I can again write it as this: F force by area and deformation, change in the dimension by the original dimension. Now this term we call it as sigma, this term we call it as strain up to elastic zone. This is up to elastic zone. I mean, at the elastic point, this will be the stress sigma E, this will be the strain epsilon E. So half sigma E into epsilon E, that is nothing but area covered under this curve in stress strain diagram up to the elastic zone. So this gives us modulus of resilience, proof resilience divided by volume. So understand, when I am trying to find area under force and displacement curve, and area under force and displacement curve, we get energy. When we are finding area covered under stress strain diagram, we find strain energy per unit volume. That is the difference between area of stress strain diagram, area under force displacement diagram. Now coming to factor of safety, as I discussed in the earlier videos in the first chapter, I said there are many assumptions in these theoretical concepts when we are deriving something. Now it is not possible every time in reality to follow all the assumptions. That means automatically the results we are obtaining will have certain amount of error depending on the kind of assumptions and the level of assumptions we are assuming. So to avoid any unnecessary incidences, we need to take some factor of safety, so that even if we are deviating from the idealness or our assumed values, there in reality there should not be any catastrophe or failure. So to avoid that, we take the factor of safety into consideration. Now how we do that is, factor of safety is, we consider factor of safety is, factor of safety value is given by actual strength of the material. This is a material property decided by material. Every material has its own actual strength. Sigma ultimate, like example, ultimate tensile strength. Say for example in mild steel it was something like this. If we are considering ultimate strength, considering the design criteria by ultimate strength, then we should take actual strength as this. If we are considering design criteria as yield strength, this will be the actual strength. That in that case, depending which design criteria we will discuss design criteria in the next class. Presently, just remember, depending on the design criteria, we will select what is the actual strength. Now, depending, every material has its own actual strength. Now, out of that, by what factor do we want to allow the strength? That is, this is allowable strength. Depending on that material only. Say, for example, this is 200 gigapascals. That is the maximum strength possible for the material. Then, for as a safety, considering factor of safety, we will see that maximum stresses generated in our object should not be, if it is an ideal case perfectly, then maximum stresses that can occur in our object can be 200 gigapascal. Till then our material will not fail. But since there are assumptions and idealness in our problem solving, and in reality that is never possible, that's why we allow our maximum stresses up to only certain limit which is less than 200 gigapascal, so that we are on a safer side. Say, for example, we are allowing only up to 150 gigapascal. That means maximum possible stresses generated due to applied forces should not be more than 150 gigapascals. That is what we are saying. So the material strength possible is up to 200 gigapascals. We are allowing the maximum stress generation in the material only up to 150 gigapascal. Then factor of safety will be 200 by 150. That means something 20 by 115, 5 4s are 5 3s are, that means 1.33. This will be the factor of safety. Now margin of safety means this factor of safety minus 1 into 100. That means here in this case it is 33%. So with this I close this lecture. In the next session, in the next video, we will start lecture 2.2, where we will discuss types of stresses, how these stresses are generated, all those things. Let's close this video here. Thank you.